Okay, welcome to lesson 22, the generator effect. So this one is really going to just be the opposite of the motor effect that we saw last time, right? So pretty much getting into this, I'll let you guys read through most of this stuff too. I'm going to kind of go through this pretty quick and get to the gist of it. So Michael Faraday, after coming up with the motor effect, pretty much inferred that we should be able to do the opposite, right? So remember, the motor effect is that we can send a current through a wire in a magnetic field and have it deflect. And now we're going to do the opposite, which should work out that if you turn motion, like you can move something in a magnetic field and have it produce a current. So that's what he figured should happen, but it took him a while to actually see this. So here was his original experiment. So what he did, so I'm looking over here, he set up a circuit, wrapped it around on this iron ring. Okay, so yeah, you have electricity going around and around this coil, right, going around that way. And what he noticed, so then you had the same type of thing on the other side, right, like coil of wire going around there to a galvanometer, which is really just, it measures current, right, like it measures a small amount of current. He turned it on, found, well, at first he noticed that like nothing happened actually, like it just didn't make any difference. But then he noticed that it actually did seem to make some sort of difference when he noticed it made some sort of difference right when he turned it on. So right when he flipped the switch open, right, the needle on this one would all of a sudden deflect just for a second and then deflect back again, which was strange, right? He didn't really understand that. But the way why it turns out to be that ends up being the case here is that this statement right here, the key element necessary for the generator effect was a changing or moving magnetic field, right? So going back to this, what happened there is when he turned this switch on for a second, right, for this coil, then it was the process of the electricity starting to go around the loops, right? It would go around and down again. That electricity going around the loops would create a magnetic field going around them, right? It would make a magnetic field going this way. And actually, I do that a little bit wrong here. It would make a magnetic field actually that was big enough to go right around those loops, right? It would actually affect these wires on the other side. And then that magnetic field would induce a current going around the other side and then deflect the needle on the secondary coil. So we'll talk a bit more about that in a second, but that's the idea. The main concept of this is going to be right here. The key element is a changing magnetic field. So yeah, make sure you guys read through that because there's also good info in there too. But here's what he found. Discovered the basic principles of electromagnetic induction. He experimented with three basic situations. So he moved a wire to the jaws of horseshoe magnet, so really changing magnetic field is what he was doing here. He plunged a bar magnet in and out of the core of a solenoid. So moving a bar magnet through that coil is a changing magnetic field. So it's changing magnetic field, creating current. And then he would touch the iron core of a coil with a bar magnet and then remove it. So really he magnetized it for a second. And when it became magnetized, the process of becoming magnetized, it would deflect that needle again for a second. So again, it only happens when the magnetic field is changing. Okay? So kind of a review of the motor effect that we had last time. Remember that if you using your hand rule, so if my fingers are pointing north to south, this is right. Fingers are going that way. I got a thumb too, I guess. And my thumb would be pointed in the direction of the electron, going that way, right? Then your force would be up. Your palm would be going up, right? Using your hand rule. Sorry for drawing. Okay. Well, what's happening in our generator effect is something similar, right? You still got your fingers that would be pointing, north to south, right? So your fingers would be going that way. Too many fingers. I got 4 fingers. 1, 2, 3, 4, right? And so everything's all still the same there. But it doesn't really work out the same way now, right? Where, it's all kind of messy. But it turns out that if I lift this wire, right, if I grab this wire and lift it upward, then it sends the electricity or the current, actually I shouldn't say current, sorry, the electrons would all be shot down from B toward A. Alright, we're going to talk more about that like in the next pages though, like how we can figure out which way it's going to go. But for now, just you can kind of see how they're similar. Okay, so Lenz's law, this is going to be a big one. So you guys got to make sure we get the concept behind this one. So the way Lenz's law is going to work is, I'm just going to go down a little bit first. It's really going to be based on this type of a situation that we have here. So if we have a bar magnet, and this bar magnet is moving toward a solenoid, then what's going to happen, and here's the statement that Lenz said. He said, an induced current flows in such a direction that the induced magnetic field it creates opposes the action of the inducing magnetic field. Okay, so that sounds super confusing, but what that really means, they're saying the induced... Okay, sorry, I got distracted there, so I forget what I was saying. So what's going to happen here is that when we're moving this bar magnet toward the solenoid, it's going to induce a current through the wire, right? Through the wire going around this solenoid core. And then that solenoid core is going to produce a north pole. Well, it turns out on that end. And what it means, what this is saying, the way we're going to handle these, is that if you if you have a bar magnet that's going to be plunging toward this thing, then the north pole, if this is the north end right here, that would make this a north end right here. Like it would always be repelling or resisting, I should say. So this would be a north pole if you were pushing in, right? Because like north and north repel, okay? And then let's see what happens here. So if that's a north pole, if that did make sense, I'm going to show some more examples too, and I think it will. But for now, if this produces a north pole right there, then what we can do is we can use our hand rule, and we can figure out, I wish you could see my hand right now, and then we can figure out which way the current is going to be flowing through this thing. So, okay, so your left hand is what we'd be using here, right? And your thumb, remember your thumb when we're doing these solenoid ones is going to be pointing toward the north pole, like so. Well, you can see, like, if you can do it with your hand right now at the same time, the way that your hand would run over this is the current, or sorry, the electrons, I should say. That's what we're doing on this one. The electrons would be flowing this way around, right? Just throwing that way. It's up and over, right? And then back up this way. That's the way your fingers are on this thing. So all of your electrons would all gather down here, right? You'd have a bunch of electrons gathering down on A. So then you could also say that this side would end up being more negatively charged. Okay? Hopefully that made a bit of sense. So I'll just show you some other ones. This is like another example of the same thing. It's actually the same picture, right? They're showing this would be a north pole, and the electron flow would be going in this direction, right? Going up and around. Okay? Okay, so there are 3 distinct phenomena that are involved in this process. So there's the action of the inducing field. So that's going to be the bar magnet being plunged in. There's going to be the resulting induced current. So that's the current going through the wire wrapping around the bar magnet. And then there's going to be the induced magnetic field created. So that is making this the north end because it's always going to repel this guy. So it's going to repel, or it's going to resist it, I should say. So, yeah, so it repels it coming in, and it would be the opposite going out. And I'll show you an example of what I mean by the going out. Okay, so if we got the opposite now, so we got, this is the north pole, and we're pulling the plunger back out again, well, what happens there is it wants to resist the motion. So now this would be a south pole. So this would be the south pole this magnet has created, because it wants to resist it, right? The south pole wants to hold that north back. It's pulling on it, right? I always kind of picture this as being like a plunger. So if the bar magnet is going in, right? So the bar magnet was going that way, then that would be a north pole because it's pushing back against it. But if the bar magnet is going the other way, then it's like the suction part of it, right? It still wants to hold on to it, so that'd be a south pole, okay? And then this would be a north pole. So then again, so now here's what we're going to do, right? So we're going to have your those are my fingers. I only got 3 of them. So those are going to be going around the other way now. So you can see that your electrons now are all going to gather on this end. See if you can do that, right? The electrons, the electricity in your fingers would go this way around, and then that way, and then around, that way, and then around, right? Okay, so hopefully you guys can do that one. It makes a bit more sense than my picture. Okay, so on this one, your electrons, well, sorry, so if you're pulling away, it's the same question. So that'd be south, that'd be north, and then try using your hand rule there. All your electrons would all gather on that end. So this would become negatively charged at B. All right. Okay, so now predicting the direction of current flow, so with straight conductors, so it's kind of going back a little bit. So what we're going to do is going to go down a little bit. So Lenz's law, we kind of figured out that's what we were showing before, right? The way that works. If we're doing so what we're going to do is called the combined hand rule. It's really rule 3 from the last one. But here's what's going to change. So instead, so if you remember on the last one, right, your fingers would point from north to south, right? So your fingers would have been pointing, this way. And then your thumb would go in the direction of the electron flow, right? It was your left hand, that'd be electron flow. It'd be right hand would be current, right? So it'd be that way. And then the force was the palm going upward, right? So that was the rule that we did. Now what we're going to do instead, we're going to change it up a little bit. It's going to be painful, this picture, so just bear with me here. I don't think I can even do this. Maybe I can. All right, so we'll see. Your fingers are still going to go in the path into the, from north to south, so the magnetic field. So your fingers are still going that way. But now your thumb is going to point in the direction of the fingers are going to point in, or sorry, your thumb is going to point in the direction of the input. So in this case, the input is actually us pulling the wire upward. That's a crazy thumb, but I want you to see how it's pointing upward, right? It's the one going in the same direction as the pulling of the wire upward, right? So it goes down, and then your palm is going to be the output. So in this case, your palm is going to be the current flowing through the wire, right? This rule will work for the generator effect and the motor effect. So from the last lesson as well, right? Because in the last lesson, your thumb goes in the input, which would have been the electron flow, and then your output was the force. In this case, it's going to be in the direction of the input, which would be the lifting the wire up, and then your palm would be the direction of the output, which is the current going through. Still the same thing if you're using your left hand. You're going to be talking about electron flow. If you're using your right hand, you'd be talking about current. It's most of the time we're going to be talking about electron flow because we're going to be talking about which end of this wire, let's say, ended up being negatively charged. So in this case, if this happened, this end would be negatively charged because all the electrons would gather down there. All right. Okay, you guys have another formula. This one actually isn't on your formula sheet though. It's not going to be a big diploma one. Actually, it probably won't even be on your diploma, but it will be on my test. So it's not one that you have to memorize, but you can write it on your formula sheet just for going into my test there. So yeah, you can tell this. So the difference between this one and our last one is that it has all the stuff for actually moving a wire, right? So there's a velocity, right? Because that's the velocity that we are actually moving the wire. That's the length of the wire that we're moving. There's the magnetic field, and then the voltage that's going to come because of that, right? One other little confusing factor here. We call the voltage that's being produced, it's going to be called, or the potential difference, same thing, also goes by the name electromotive force. Not a force, but we call it that anyway, so just to confuse you, so just try to remember that one. Okay, so I'm going to let you guys look through those and try those type of questions. So then electric motors, if you guys can think back, like way back to grade 9, an electric generator, sorry, I think I said motor, electric generator, is going to be a loop of wires rotating in a magnetic field. That's how really all generators work. So for like a hydro dam or a coal fire plant or anything that's producing electricity, even nuclear power generators would still, they actually just make steam and then they turn a coil of wires in a magnetic field and create alternating current or current. All right, practice problem. So see if you guys can try these ones. I really hate drawing my hands here, so like, I'll try not to do that. But so we've got the north pole coming in. That's going to turn this into a north end, right? Because it's going to resist. So if that's a north end, and the question's asking which end will become negatively charged, it's going to be the easiest to use my left hand on this one. So point your thumb at the north pole. Figure out which way your hands wrap around this guy. So if that's the left, if that's your left hand there, it turns out that the electron, you should see that your fingers wrap around this way, going around. So your electron should be gathering on that end. So this would become the negatively charged end, so B. Okay, number 2, determine the direction of the induced current for the following coil. Is A positive or negative? Okay, so in this case, we're pulling the north end away, right? So this is my north end. So that would make this my south end. That's where I start on this one, which would make that my north end. The word induced current instead of electron is a hint there. This should be your right hand. So your right hand, right? So if you do this one, so remember thumb pointing this way with your right hand, your fingers would end up wrapping this way around, right? And that would make all of your, well, current in this case, so all the positive things, right? And your potential, it's like this end is becoming all positive because that's your current flow, right? Which would make this end my negative end. Okay, number 3, determine the pole of the bar magnet. Oh, already kind of giving away the answer. See if we can find it again. Determine the pole of the bar magnet that is being inserted into the illustrated induction coil. So this one's kind of the opposite. They're just giving us the other one first here. One clue here, that I, that means current. So which hand are you using? Right hand, right? So right hand is current. So your hand would go around the back side. Like picture your hand going around the back side of this bar magnet. Right? So then if that's the case, I'm using my right hand, my hands are looping around that way. Your thumb right now, if you're doing this, should be pointing this way, which means that's the north. And that would be the south. And if that's the south right there, and I'm plunging this bar magnet toward it, well, it always repels, or it always resists, right? So that would make this the south. South and south don't like each other, right? They repel, so they're gonna resist each other. So that must be the south end of that. All right, which end of the conductor will become negative? So this is using your combined hand rule. So which one will become negative? So in that case, it's probably going to be the easiest just to use my left hand, right? See, we'll figure out which way the electrons are going. So your fingers go from let's see if I can draw this, will go from north to south, okay? And then your thumb is going to go down, right? Because that's the direction that the wire is being pulled. So this is all filled in, right? Because of the back side of my hand. You can see that my palm would be pushing those electrons up to A. Again, sorry for the picture. Okay, so all my electrons would come down to that end. So then A would end up being negatively charged. Okay, these ones. So what's happening here? When it says which way will the electrons flow in the circuit below? First off, what's actually happening here is this is just like here is like a bare wire, and that's a bare wire, and really this is just a bare wire too, right, or bare conductor. So what's going to happen is if I move this conductor through this magnetic field that's going into the board, like to the right, then that should induce a current, right? So depending on my hand rule, or depending on what we're doing here, it's either going to cause electrons to, it's either going to cause electrons to go around this way, or it's going to cause electrons to go around that way, right? So we got to figure out which one it is. So your fingers right now, or you should have your left hand because it's electrons. Your fingers should be going into the board, and your thumb should be pointing in the direction of that arrow, right? Because that's the direction you're moving that thing. Well, then your palm should be down right now, and then that would cause the electrons to all go this way. So your electrons would be going this way around the circuit, and so they're going counterclockwise, right? All right, which end of the conductor will become negative? So now the dots here mean that it's coming out of the board, and we want to know which way it's going to be negative, so I'm going to use my left hand again. So your fingers should be pointing out of your paper right now. Your thumb should be in the direction of that motion, which would make your palm pointing down, which means that your electrons are going to go down. So all your electrons would gather on the end of that wire. So the bottom would become negative. Okay, this one, I'm not going to do this one. Look back to that question. I think you guys will be fine. It's really just plugging the numbers in. Just make sure you change that into meters. Yeah, you should be good. Look back a couple pages and find it's just that one formula for that one. And then again for this one, I think you guys will be good on this one too. You're just using this formula, right? V is equal to B velocity L sine theta. And the only little quirk here, we'll read it. It says the conducting rod in the diagram is 15 centimeters, so that's this one. Long and is moving at a speed of 4 meters per second, perpendicular to a 0.3 Tesla magnetic field. The conducting rod slides across two wires which form a circuit. If the resistance in the circuit is 4 ohms, and we haven't really talked much about ohms, what is the magnitude and direction of the current through the circuit? Okay, so what it turns out, since it is perpendicular, right, so it's perpendicular, we don't actually need the sine theta part of this, right, because sine of 90 degrees is just 1. But we have this, and we have this. Well, plug them all in, change that to meters first though, right, for your length, and that will give you V, okay? Now that you have V, we're looking for current, right? So current. So, and they've given us the resistance, right? So ohms. So rearrange, solve for I. Okay? So you should be able to check your answer there. So okay, so I'm gonna leave it at that. Hopefully that all made sense. Come find me if it didn't.